Throughout this course, the concept of aerodynamic noise, such as turbulence interaction noise and also turbulent boundary layer triangulation noise, should appear quite often. And what do they have in common? It is turbulence. And it is indeed an unfortunate fact that turbulence can be easily found in various engineering systems, and it is often responsible for generating aerodynamic noise. Turbulence interaction noise, as its name suggests, is the result of turbulent inflow impinging onto an aerodynamic body. This can be found, for example, inside a turbofan, a type of engine that powers most of modern airliners today. Inside a turbofan, there is this rotating fan that drives a huge amount of air inside the engine, leaving a trail of turbulent wake behind it. Now, downstream of this fan is a set of non-rotating blades, known also as the stators, whose function is to recover the swirling motion inside the fan wake, which would increase the performance of the engine overall. Now, the process of impingement of this turbulent fan wake onto the stators will result in a loud noise being generated. And in fact, this process will only become more relevant in the future as the size of the turbofan increases in order to pursue even higher efficiency. Now, turbulence can also be produced by the aerodynamic body itself, such as inside the turbulent boundary layer. And when this turbulent boundary layer encounters a sudden change in surface condition, such as at the trailing edge of an airfoil, loud noise will be generated as the result of acoustic scattering. And this is one of the main noise generation mechanisms on a modular wind turbines. And in fact, as the size of wind turbines are also increasing in order to produce more energy, this issue will also becoming more and more important. And thus, this is why it is quite important for us to identify suitable noise mitigation techniques at the early stage of design if possible. And in this video, I will be showing you how we have been applying permeable materials in order to tackle these issues. Permeable materials imply that flow is allowed to enter into it. And this is why they can be considered a sort of intermediary condition between free fluid and a fully solid material. Now, considering that aerodynamic noise is often the result of turbulence encountering a sudden transition from free fluid to a solid body, and this is why permeable materials might be useful in these circumstances. And in the following, we have been applying this aluminum metal foam here in various applications. And to begin with, I would like to first show you how we've been applying this permeable material for mitigating turbulence interaction noise. This is the rod airfoil configuration. We can adjust the Reynolds number based on the rod diameter such that the rod will produce this turbulent wake that contains alternating vortices that are also referred to as the common vortex thread. Now, when this common vortex thread impinges onto the airfoil downstream, loud noise will be produced. And this noise can be characterized by these tonal peaks that correspond to the vortex shedding frequency and also a certain amount of broadband noise component. And in this example, we have replaced the first 15% of the airfoil leading edge with another one that is made out of the metal foam. And with this permeable leading edge, we have been able to obtain a broadband noise reduction of up to 3 decibels, although the tonal noise reduction is rather small. The noise attenuation level has been found to be proportional with the reduction in leaf fluctuations level, which indicates that the distortion of the vertical structures impinging at the airfoil leading edge has become less severe when the permeable leading edge is being used. Now, we have also attempted to improve the noise reduction further by combining the permeable leading edge with serrations. In fact, we have found that the permeable serrations perform even better in terms of noise reduction compared to the regular solid serrations. Now, using this serration platform, we have basically allowed the source distributions along the airfoil span to become decorrelated. What this means is that now this distribution of sources, instead of having them emitting noise in unison, we allow them to behave more erratically, which is particularly useful for tonal noise attenuation. Now let's look into the application of permeable material to address trailing edge noise. In this example, we have been applying the metal foam insert to replace the last 20% of the cord of a NACA 0018 airfoil. And to generate turbulent boundary layer on this scale model, we have been applying zigzag tripping devices near the leading edge. Using this permeable insert, we have found that a noise reduction of up to 10 decibels could be achieved primarily at low frequencies. However, this noise reduction level gradually becomes smaller as the frequency increases, and eventually there is a slight noise increase in the high frequency range. And this noise increase can be attributed to the rough surface of the metal form. Using high fidelity numerical simulations, we have found that acoustic scattering takes place all across the surface of the permeable insert, although the strongest ones are located at the solid permeable junction and also at the actual trailing edge. Nevertheless, the acoustic scattering efficiency of the permeable insert is lower compared to the regular solid trailing edge, leading to noise reduction. However, this benefit requires the permeable insert to be fully permeable. If someone were to introduce a solid partition along the center line of the permeable insert, effectively blocking all kinds of flow communication between both sides of the trailing edge, then this noise reduction capability will become completely gone. The applications of permeable materials for aerodynamic noise mitigation is still an actively investigated topic even today. There are still many more questions that are left unanswered. One such problem is about upscaling from laboratory scale model to the real thing. Some of our more recent studies are also focusing into obtaining optimization strategies for new implementations and applications. And with better understanding of the physical mechanisms behind the permeable materials, we will be able to obtain better applications in the future for different kinds of aeroacoustics problems. I'm Christopher Teruna, a member of the Aeroacoustics Research Group at the Delft University of Technology, signing out.